Today, we're going to be looking at infrared spectroscopy and mass spectrometry. And I'm going to start by sharing my screen. Okay, in my research, sometimes I or my students will discover new compounds that no one else has made before. And if we want to publish, we need to be able to prove that that is what we've made. And one way of doing that is using spectroscopy. Spectroscopy is a technique that's used to determine the structure of a compound. There's many different types of spectroscopy. We're going to look mainly at infrared and also mass spectrometry in this chapter. Most techniques are non-destructive. They destroy little or no sample, and they involve absorption. Absorption spectroscopy measures the amount of light, or more broadly, electromagnetic radiation, absorbed by the sample as a function of wavelength. All right, we'll look at the first two items in this chapter. Infrared spectroscopy measures the bond vibration frequencies in a molecule and is used to determine the functional group. Mass spectrometry fragments the molecule and measures the mass. MS can give the molecular weight of a compound, functional groups, and sometimes the molecular formula. Nuclear magnetic resonance, or NMR, analyzes the environment of the hydrogens in a compound, and this provides useful clues to the alkyl and other functional groups present. Ultraviolet spectroscopy uses electronic transitions to determine bonding patterns. Electromagnetic radiation travels in waves. The frequency, nu, of a wave is the number of complete wave cycles that pass a fixed point in a second. Wavelength, lambda, is the distance between any two peaks or any two troughs of the wave. Frequency and wavelength are inversely proportional. Okay, if we multiply them together, we get the speed of light, c, which is 3 times 10 to the 10th centimeters per second. Energy is proportional to frequency, but it's inversely proportional to wavelength. Energy equals h nu, where h is Planck's constant. Here is the electromagnetic spectrum. Okay, electromagnetic radiation covers a huge range of wavelengths, from very small gamma rays to very large radio waves. Radio waves can have wavelengths the size of one or more football fields. Okay, up at the top we have gamma rays. Gamma rays are emitted from very reactive, unstable radioactive isotopes that come out of the nucleus. They're very penetrating. It takes lead or concrete to stop gamma rays. X-rays are the result of transitions involving inner or core electrons. And X-rays are less penetrating than gamma rays. As you know, X-rays will penetrate soft tissue but not bone. Okay, then we have the ultraviolet and the visible. These are the result of electronic transitions, usually outer or valence electrons. The color of fireworks is the result of these electronic transitions. When an atom is heated up, its outer electrons jump up to an exciting excited state, and as they move away from the heat source, they cool, jump back down to the ground state, and emit a photon of visible light. And different elements will emit different colors. In this chapter, we'll look at infrared radiation. This involves transitions of molecular vibrations. Microwave radiation involves absorption of energy, which results in excitation of rotational motion. A microwave oven is tuned to the excited state of water. So water molecules absorb microwave radiation, they rotate faster, they produce friction, which produces heat. In the next chapter, we'll look at nuclear spin transitions, which involve very low energy in the radio frequency region of the spectrum. Right, the infrared region is just below the visible region and just above the microwave and radar frequencies. Wavelengths are usually from 2.5 times 10 to the minus fourth to 25 times 10 to the minus fourth centimeters. More commonly, though, wave numbers are the units of choice. These are reciprocal centimeters, or waves per centimeter. Wave numbers are proportional to frequency and energy, unlike wavelength. Right, we can think of atoms that are covalently bonded as being like balls connected by springs. Okay, these springs can be stretched and compressed, and the restoring force will push the two atoms apart, and then the atoms vibrate until equilibrium is restored. Okay, this is a very abbreviated table of bond stretching frequencies. Okay, it shows a couple of different points here. Okay, frequency decreases with increasing atomic mass. Okay, so we have a CH bond, which vibrates at about 3,000 wave numbers. We have a deuterium, heavy hydrogen, with a mass of 2. That's vibrating at about 2,100 wave numbers. And then a carbon-carbon bond vibrates at around 1,200 wave numbers. Okay, frequency increases with bond energy. Okay, so a triple bond is more energetic than a double bond. So when it stretches, it does so at higher frequency and higher energy. Okay, so these are some characteristic frequencies of single bond, double bond, triple bond. Okay, we see the same thing for CN and CO bonds. Okay, the stronger the bond, the higher the stretching frequency. Okay, water has 3 vibrational modes. Okay, and these are described as symmetric stretching, where the OH bonds are stretching in unison, asymmetric stretching, and scissoring. Okay, no two molecules will give exactly the same IR spectrum except enantiomers. The fingerprint region is between 600 and 1400 wave numbers and has the most complex vibrations. We're actually going to spend most of our time on the region above that. Because these molecules will have unique infrared spectra, crime labs and environmental labs will have libraries of spectra, and they will take an infrared spectrum of some material that's gathered in evidence, and compare that to what is in the library. Okay, much like a fingerprint is compared with a database. Okay, the strongest infrared absorptions occur where we have a permanent dipole moment. For example, in HF. Okay, if there's a change in dipole moment when the bond is stretched and compressed, then we see a stronger infrared absorption. Okay, here's a very crude diagram of the old style infrared spectrometer. Okay, we don't use this type anymore, but we have a glowing wire. Okay, this is a lot like the coils in the toaster. You pass an electric current through a resistive material and it glows red hot. It gives off infrared radiation. You have a reference and a sample beam. A monochromator, which selects out narrow bands of frequency, and then that reaches the detector. Okay, what we actually use and what most chemical laboratories use nowadays is an FT-IR spectrometer. Okay, this has better sensitivity. Less energy is needed from the source. Instead of selecting a very narrow region of the spectrum at a time and sweeping it, okay, we have all the wavelengths available at once. Okay, we can complete a scan in 1 to 2 seconds versus 15 to 20 minutes with the old type. Then we can take several scans and we can average them. Okay, and that averages out the baseline noise. Okay, and then uses a laser beam to accurately measure the distance between the moving mirror and the fixed mirror. Okay, and then it uses a mathematical operation called a Fourier transform to translate the data into a spectrum. Okay, so the FT operation converts this interferogram to a spectrum. Okay, this is a spectrum of normal octane. And on the x-axis, we have wave numbers. Here's the fingerprint region that's shown. The y-axis is what is called percent transmittance. Okay, so at this frequency, okay, no infrared radiation is being absorbed by the sample. But when we get down here to about 3,000, okay, that excites CH stretching frequencies, and since the molecule will absorb that to excite these frequencies, less infrared radiation will reach the detector, and we see a drop in transmittance. Okay, and then we have a few other modes. We have the CH2 scissoring, we have the CH3 rocking, for example. Stronger bonds absorb at higher frequencies because the bond is more difficult to stretch. Okay, so a CC triple bond will be just below 2200 wave numbers. A CC double bond will be about 1660, and a CC single bond about 1200. Conjugation lowers the frequency. Okay, conjugation, that is alternating double bond, single bond, double bond. Okay, so if we have an isolated carbon-carbon double bond, that absorbs between about 1640, 1680 wave numbers. But if it's conjugated, that lowers the frequency by about 20 to 40 wave numbers. And then an aromatic CC will be about 1600. Okay, if we have a conjugated diene such as this, these double bonds will have some single bond character, so they'll be longer than a typical isolated CC double bond, and therefore will have lower frequency. Okay, different CH bonds will absorb at different frequencies depending on the hybridization of the carbon to which they are attached. So a greater percent S character in the hybrid orbitals will make the CH stronger. Okay, so an sp hybrid carbon will have 50% S character, and it absorbs at 3300 wave numbers. It gives a sharp absorption. Okay, an sp2 is 1/3 S character, so it has less S character. It absorbs just above 3000, whereas a hydrogen on an sp3 carbon will be just below 3000. Okay, so if we have an alkane, such as normal octane here, this will only show stretching and bending frequencies for CH and CC. Okay, we won't see much else. We'll see the CH stretch and actually not much in terms of the CC. Okay, last bullet point is significant. In this example, the importance lies in what is not seen, that is the lack of bands, which indicates that there is no other functional group. Okay, here we have an alkene. Okay, let's compare. Okay, here's the alkane. Okay, we've got some additional bands for the alkene. Okay, this is the alkane CH stretch, and this is the alkene CH stretch, just above 3000. Okay, we also have an additional CC double bond stretch, and then we've got some more CH bending. Okay, the main thing here is this alkene CH stretch and the alkene CC stretch. Okay, we can look at that and tell that it's an alkene. Okay, so this is hex 1-ene. Right, here's a couple of different alkynes. This is oct-1-ine. Okay, we have the very distinct alkyne CH stretch at 3313. Okay, remember the alkene was just above 3000. And then we have the CC triple bond stretch at 2119. Okay, and then here we have oct-4-ine, okay, a symmetric molecule. And there's no alkyne CH stretch because there's no alkyne CH. There's also no CC triple bond stretch. Because of the symmetry, we're not changing the dipole moment as this stretches, and so that doesn't show up. Right, OH and NH stretch both occur at about 3300, but they look different. We can distinguish between them. The alcohol OH is broad with a rounded tip. A secondary amine is broad with one sharp spike. A primary amine, RNH2, is broad with two sharp spikes. And if there's no NH, then we have a tertiary amine because there's no hydrogen. All right, so here's an alcohol, and we can very clearly see the difference between this and the alkyne. The alkyne was very narrow. This is broad with a rounded tip, okay, because of hydrogen bonding. That causes the broadening. And then almost everything will have this saturated CH stretch. Okay, here's an amine. Okay, the NH stretch is often not as intense as the OH. It can be more intense than this, but it's usually not as broad as the OH. So this is a secondary amine. There's one NH peak. Okay, primary amine. Right. For primary amine, we would have two spikes, something like this. Okay, this is because of symmetric stretching and asymmetric stretching, where the NH bonds are stretching, compressing in unison, or if they're if one is stretching while the other is compressing. Right, the carbonyl stretch, okay, because of its dipole moment and the fact that stretching it causes a change in the dipole moment, the carbonyl is almost always very distinct, very intense. The carbonyl occurs in a number of different functional groups, including ketones, aldehydes, and carboxylic acids. And notice the CO stretch is about the same frequency. Okay, but we can distinguish among ketones, aldehydes, and carboxylic acids by looking for other stretches. Okay, for example, the aldehyde will have two bands at about 27 and 2800. Okay, as a result of the aldehyde CH stretch. This is a little bit lower frequency than the alkane CH stretch, and of course this will be absent in the ketone. The carboxylic acid will have a very broad OH stretch. Okay, it will be lower frequency and usually quite a bit broader than the alcohol CH stretch. Okay, so here is a ketone. Okay, here's the saturated CH stretch at around 2900 to 3000. Okay, here's the very distinct carbonyl stretch at 1718. Okay, let's compare that to an aldehyde. This thing called an overtone, that is a multiple of this very intense stretch here. Okay, the aldehyde has these two additional bands from the aldehyde CH at 2720 and 2820. Okay, and here's a carboxylic acid. Okay, it also has the carbonyl. The OH you can see is very broad, and in fact it's superimposed on the CH stretch. Okay, whereas an alcohol will have the CH and OH stretches distinct from each other. Okay, we said earlier that conjugation lowers the frequency. That's also true for carbonyl compounds. Okay, so a normal aldehyde or ketone or carboxylic acid shows up at about 1700. Okay, here are some examples of conjugated systems. Okay, this explains why we have a resonance form where the CO has some single bond character, so that lowers the frequency. Okay, so this conjugated ketone, 1685, This conjugated aldehyde 1690. And this carboxylic acid is conjugated with the benzene ring, 1687. Okay, resonance is a very significant factor in amides. Amides will have a considerably lower frequency for the carbonyl, 1640 to 1680. The CO bond has considerable single bond character. Right, and then here is butanamide. We have the two NH stretches from the primary amide. Okay, these are narrower than what we'd see for an OH. We've got the alkane CH stretches, and then we have the carbonyl, and instead of being around 1700, it's about 1630 to 1660. Okay, so aldehydes, ketones, carboxylic acids will absorb about 1720. Conjugation lowers the frequency. Esters typically will have a little bit higher CO frequency. They typically absorb about 1735 or sometimes a little bit higher. Another factor that causes carbonyls to absorb at higher frequencies is strain. Okay, so here we have cyclobutanone, so that will raise the CO stretching frequency. Okay, here are some carbon-nitrogen stretches. CN stretches are usually strong, and we have two triple bonds that absorb around 2200. The nitrile will usually be just above 2200, whereas the alkyne will be just a little bit below 2200. The nitrile is often strong. Okay, we're causing a change in the dipole moment as we stretch this. The CC triple bond is usually moderate or weak. Okay, so here's a nitrile, butyronitrile. We see the CH saturated stretch, and here's the nitrile CN triple bond. Right, here's a summary of IR absorptions. NHOH and CH are in this region. Triple bonds are in this region around 2200. The double bonds are between 1800 and 1600, and then below 1400 we have the fingerprint region. Okay, so while alcohols, amines, and amides and alkynes will all show up in the region around 3300, the alcohol is always broad. The NH may be broad, may be sharp, or may be broad with spikes. The alkyne is always sharp and usually strong. Okay, so we can easily tell an alkyne CH from an OH. Okay, saturated CH stretches will be just below 3000. Alkene CH stretches just above 3000. Carboxylic acids will be centered on around 3000, but they'll be very broad. Okay, and as I said before, alkyne CC triple bond stretches will be just below 2200, whereas the nitrile will be just above. Okay, carbonyl stretches are typically very strong, and ketones, acids will be around 1710, aldehydes around 1725. Esters will be higher, amides will be lower, And if there's conjugation, that will lower the frequency. Okay, and then we have some other characteristic bonds that show up around 1660. Right, so let's determine the functional groups in this compound. Okay, it doesn't look like we have OHs or NHs. Okay, we don't have a nitrile or an alkyne. Okay, we do have a carbonyl that's showing up at around 1720. And we have these two peaks here at about 27, 2800. Okay, so this would likely be an aldehyde. Okay, and that's what it is. Okay, IR alone cannot determine a structure. Okay, we can tell that it's alcohol or a carboxylic acid or a ketone, but we can't tell necessarily which ketone or which carboxylic acid, for example. Some signals may be ambiguous, especially at the lower frequencies. We can usually tell the functional group. We can also look for the absence of a signal. Okay, that's what I was doing earlier. We could see there was no triple bond, there was no OH or NH. And crime and environmental labs and testing labs will typically compare a known sample's IR spectrum with the measured spectrum. Okay, we're going to take a break here, and we'll come back shortly and look at mass spectrometry.